Hey guys, welcome back. This is going to be part two of the review for energy with calculus. So we left off with this one where we had a potential energy function. And, we know when it's located at 0.5 meters, its velocity is 2 meters per second. And we know that all forces acting on it are conservative. So that's going to tell us that we have that our energy is conserved. So the total mechanical energy is going to be equal to the potential energy plus the kinetic energy. So at negative 0.5, this is going to be 4. Negative 0.5 squared. K is going to be 1/2 mv squared. And this is going to be 1/2 3 kilograms times 2 meters per second squared. So that's 4 times 3 is 12, divided by 2 is 6. So I have 6 joules of kinetic energy at that moment. And I have 1 joule of potential energy, right? Because 1/2 squared would be 1/4, and 1/4 times 4 would be 1. So that's 7 joules of total energy. I want to calculate the x-coordinate where the object would have 0 kinetic energy. So that would mean that all of my 7 joules would have to be equal to 4x squared. So I would have 7 over 4 square rooted would be the location. And that would be plus or minus. So I have plus or minus radical 7 over 2 meters would be our answer for that one. Assume that the magnitude of force applied by the spring is of the form f of x equals ax squared. Calculate the work done by the cart in compressing the spring 0.1 meters from its equilibrium. So work is going to be F dr integral, and so I'm going to have the integral of ax squared dx from 0 to 0.1. Do I know what a is? I guess I'm just going to have it in terms of it. All right, so this is going to be ax cubed over 3 from 0 to 0.1. And so I'm going to have a negative 1 cubed minus 0, right? That's over 3. So this is going to be 0.001 over 3 times a. Calculate the speed of the cart just before hitting the spring. I feel like I don't know what the mass is, but I can just say that this 1/2 mv squared is going to be equal to 0.001 over 3 times a. So I would just be getting v by itself. I feel like we're missing something in this problem. Or it's parts of 2 different problems. So we would just get v by itself. Square root. All right, we did this problem previously, I think. But it's good to relive this, and we can see how this is related with the energy and with the power and with the network. All right, so we have an equation that is x equals 0.5 t cubed plus 2t, where x is in meters and t is in seconds. determine the speed of the box at time t equals 0. So b is going to be dx dt. And so this is going to be 1.5 t squared plus 2. When I put in 0, that's going to cancel out. So it's going to be 2 meters per second. If I want to get the kinetic energy is going to be equal to 1/2 mv squared. So this is going to be equal to 1/2 m times 1.5 t squared plus 2 squared. I can put in the m, so I get 50. The net force acting on the box is going to be equal to ma. So a is going to be equal to the derivative of the velocity function with respect to time. So I'm going to have the derivative of 1.5 t squared plus 2 dt, and I get an acceleration that is 3t. And then if I plug that back into our equation, f net is going to be equal to 100 times 3t. So that's going to be equal to 300 t. Power would be equal to the force times the velocity. So this is going to be 300t times our velocity function, which was 1.5 t squared plus 2. Net work done on the box is going to be the integral of, we don't have distance. We do have distance, right? The integral of dx, of f dx. Everything's with respect to dt, so that's not going to work. But I can do change in kinetic energy. So I'm going to have 1/2 mv squared minus 1/2 mv squared. Our kinetic energy is equal to 50, 1/2 t squared plus 2. So this is 50, 1/2 t squared plus 2 squared. So at 2 seconds, if I plug in 2 for this, I'm going to get 4 times 1.5 is 6, plus 2 is 8, squared is 64. 64 times 50 is going to be 320 joules. And then at 0 seconds, I'm going to get 2 squared, which is 4 times 500, which is going to be 200 joules. So the net work done is going to be positive 120 joules. Indicate below whether the work done in the box by a student is greater than, less than, or equal to the answer. The work would be greater than. It is a rough surface. So there is work done against friction and work to increase kinetic energy. And together, that is the work done by a student or a child. AP stick figure.